How do we know how to change our values of weights and bias to reduce the cost? It turns out that the important concept here is the change in cost per change in bias that I mentioned before. What we have here is the concept of how much the cost changes per unit change in parameter value. We can write this as delta costs divided by delta bias. If we extrapolate these changes to infinitesimally small values, we end up with a concept of a derivative, which can be represented as d cost over d bias. The derivative of a function tells us the slope of the function at a given point. This is how much the function is changing as a function of a change in its variable. Notice as how we approach the bottom of a function, which is a local minimum value, the slope of the function becomes 0. And this means that the derivative is 0 at that point, and we're at a local minimum. To minimize a function, we need to go in the direction of the negative derivative, which is the slope of the function. So if we're at a point where this slope is negative, this is the direction we want to go in. So we keep taking positive steps in our parameter value. But if the derivative is positive, we need to go with the negative derivative. So this means we have to go now in the negative direction of parameter value. Even though in our example we just showed changing the value of the bias, in reality, of course, we have many parameters to update. We have all the weights and the bias for a single neuron, and we have to do this for all the neurons in our network. So we need to expand the idea of a derivative to more than one variable, which gives us the concept of a gradient. Gradients are the derivatives for multidimensional functions. When we have multidimensional functions, which are functions that depend on more than one variable, each variable represents its own direction in mathematical space. This means each variable is representing its own orthogonal direction. Orthogonal means the direction is at right angles to all other directions. So if there are two variables, the two directions define a flat surface, and if there are three directions, the three directions will define a three-dimensional space, and so on, but after 3 dimensions it becomes hard to visualize, but the same idea continues. Each individual derivative for each variable tells us the slope of the function in that direction for that variable. And the negative slope tells us how we want to change that variable to go towards the minimum of the function. So the gradient is the combination of all these individual derivatives together. Taking different size steps in different directions results in being equal to a single step in a combined direction, which is the direction of our gradient, which is why we talk about the gradient as having a direction. However, it can be easier just to think of the gradient as the set of individual derivatives, which are the changes we need to make for each individual variable. In our case, we're taking the gradient of a cost function. Our variables are our neural network parameters, which are the weights and biases of all the neurons in our network. So each weight and bias has its own derivative at any given point, where the given point is defined by the current value of all weights and biases. So the gradient is just the combined set of all the individual derivatives for every weight and bias, and it tells us how much we want to change every weight and bias in order to minimize the cost function. So the negative gradient tells us which direction to go to minimize our cost function. And minimizing our cost function minimizes the difference between our model's predicted outputs and the actual outputs we want our model to have. So that's how we can proceed with learning, is to go in the direction of negative gradient in order to minimize our cost function. I want to just emphasize here that we're looking at how changes in our model parameters, which are the values of weights and biases, change the cost function. We're not looking at how the data inputs change the cost function, because our data is actually fixed here. We have a fixed training set over which we're evaluating our cost function, but that data is fixed, and we don't have the option to change our training data. We are changing our weights and biases. And so our gradients are calculated with respect to the values of weights and biases. In this case of having more than one parameter, our gradient, which is our direction of steepest change, is defined by how much one parameter changes the cost function compared to how much another parameter changes its cost function. And so learning by going in the direction of the negative gradient, which is also the direction of the steepest descent towards the minimum of the cost function, is known as gradient descent. Gradient descent and small variations on gradient descent are how neural networks learn.